Hi, my name is Kristín Jónsdóttir. I work at the Icelandic Meteorological Office as the team leader for the Natural Hazard Operational Monitoring, which means that I am in charge of the team that's doing the shifts for the operational monitoring of natural hazards. For the real-time monitoring, we are using seismic streaming of data, and today we are going to talk about how we use this seismic streams and the tremor to monitor an ongoing eruption. We will be looking at an example from the Fagradalsfjall eruption and how we were monitoring the eruption using seismic instruments. Now, if we look at the map, we see that there are orange triangles marking the seismic stations. And one of the stations is actually inside the orange field there, which is showing us the lava field. And unfortunately, we lost this instrument as lava actually ran over it. So this is something we also need to think about when we are doing volcano monitoring, that we want to be close to the eruptive activity to not miss anything that's ongoing. But still, we have to also make sure that our instruments are safe. So this is one of the challenges. Now, one of the instruments, the blue triangle there at the bottom, was moved to a new site just to prevent this from happening. So at least that one is safe. And if we look at the top instrument here, we are going to look at some examples of the tremor that has been recorded at that station. On this station, we are looking at the tremor that was recorded for a whole month from the beginning of the eruption. And we are seeing different things on this plot. So the vertical axis is showing the amplitude of the tremor, which means essentially just how much the seismometer was shaking. And the three different colors that we see here show how much shaking there was within different frequency bands. So the blue color here represents frequency between 2 and 4 Hz, which is the highest frequency. Green one is the middle frequency between 1 and 2, and the lowest frequency between 0.5 to 1 Hz. So this is a very common way of plotting a long time series of the seismic amplitude, and this technique is called RSAM. And now what we see here, on the 19th of March, we have an increase of the blue signal here, showing us that when the eruption started, there was a clear increase of tremor and most at the highest frequency. About a week later, we see a dramatic decrease in the tremor, and this was when the crater collapsed. And when the crater collapsed, there is a pressure decrease in the system. So the pressure decrease is pronounced by a dramatic drop also in the tremor amplitude. So after the crater collapse, there is a slow build-up of the crater itself, and as it builds up, there is also a pronounced increase in the tremor amplitude. Now, about a week later, we see certain drops in the amplitude. And these are not caused by crater collapse, but it is caused by the opening of new fissures. So we could actually learn from this and provide information to the civil protection. And when we saw drops like this was actually indicative that new fissures were about to open. And we made a couple of warnings about this, which were successful, which was very good. So up until May, the activity was quite continuous within the erupting crater. But in May, we started to see something which was quite peculiar. We started to see lava fountaining and pulsating of the activity, as these photos show. So we had a few minutes of no activity and then a few minutes again with lava fountaining, and really high lava fountains, even up to 300 meters high, and which we could see very clearly here from Reykjavík. these lava fountains were also reflected in the tremor. So both the lava fountaining and also the break between them, as you can see here. So again, we are looking at data, tremor data, RSAM data. So this is averaged amplitude. And we see a couple of hours here on the 2nd of June from various stations. So all the stations are showing the same. They are showing us when the lava fountain is ongoing. This is when we have high pulses, so high tremor, followed by this drop. So in the tremor plot, we have a very good overview and a recording actually of the lava activity within the crater. We can look at the data in a different way. We can also look at spectrograms. So spectrograms show us the frequency content of the seismic data. What we see here is just 1 hour from one station, Maree, which is very close to the erupting activity. And on the y-axis, we have the frequency content, so from 0 to 50 hertz. The green colors here show us the lava fountains themselves. So these are times when we have lava fountaining and at the same time high amplitude of the seismic data. So you can see that there are 6 lava fountainings happening within that hour, and each lava fountain takes about 4 minutes each. Today the situation is a little bit different. We still have pulsating activity, but the pulses have become much longer. So the activity goes on for about 10 to 20 hours, and we have also longer breaks between. So if we take the time between the highest activity, the hours are about 30 to 40 hours. We do not have high lava fountains like we had before, but we have clear activity within the crater. Today's activity is also clearly visible in our seismic data. And here we are again looking at the tremor, the RSAM data from station FAF, and we are looking at the last 72 hours. There are some details also that we are curious about, and this is, for example, the asymmetry of these pulses. So we see this increase, so there's quite a slow increase of the activity, but we always have this clear drop of activity, which almost looks like there's something wrong with the sensor. But this is the true activity, so it really looks like somebody has turned off the kettle. So looking at the latest data there, we can see that there is activity ongoing. And we can also go back to this data to speculate a little bit how is it likely that the next 24 hours are going to be. So it's good to look at this data before we plan a visit to the eruption site. Here again we are looking at the same station, but now we are looking at a whole month. And this is actually the last month that we have. And here we can very clearly see the pulses. So for the last month, we have about 19 pulses, which means that 19 times during the last month, we had erupting activity within the crater. At the end, I would really like to show you some new science that we are looking into. And this is using fiber optic cable instead of a normal seismometer. So we are using the cable to measure the seismic tremor. In cooperation with ETH, we used a cable that goes from the parking lot up to Langihryggur, and you see it here on the map with a white line. So let's look at the video of our data. We see the time on the y-axis, and then we see the distance along the cable on the x-axis. So the cable is actually connected back and forth. So it goes from the parking lot to the Langihryggur and then back again. So what we see now are some vibrations. So this is actually showing us the lava fountaining, and what we see are coherent signals being measured along the cable. We were quite happy with this and to see the coherent signal going across the fiber optic cable, because this is the first time we know of where we have such a recording of volcanic eruptive tremor on a fiber optic cable. To summarize my talk, firstly, it's important to have your seismic instruments close to the erupting activity, but not too close, because you don't want to lose them. And you have to be prepared to actually move them if needed. Secondly, it's very important to look at the tremor data and not only look at the past 30 minutes or so, but always look at the long-term activity because it can be reflecting the volcanic behavior. And thirdly, it's important always to look at the latest technology and see how you can improve. If you want to know more about seismic tremor and monitoring, please look at these references.